Welcome to another tutorial class in our video lecture series on design of reinforced concrete structures, and today we will look at a numerical regarding the design of singly reinforced beam. You can see the question on your screen here. Design a simply supported reinforced concrete rectangular beam whose center to center distance between supports is 8 meter and supported on brick walls of 300 mm thickness. The beam is subjected to imposed loads of 7 kN per meter. So we are given that this beam here is simply supported whose center to center distance between the supports is 8 meter or 8000 millimeters. The supports are 300 mm thick brick walls and the beam is subjected to imposed loads of 7 kN per meter. So to proceed with the solution, since this is a design problem, the parameters that we have to determine are the width of the beam, the effective depth of the beam, the total depth of the beam, the percentage of steel reinforcement, grade of steel, and grade of concrete. So you have to remember that these parameters have to satisfy different requirements, and also these parameters are interrelated. That means when we determine one parameter among them, then another parameter may need revision based on the determination of the previous parameter. So let us first begin with assuming the grade of steel and the grade of concrete. We will assume the grade of steel to be used in this reinforced beam will be Fe 415 and the grade of concrete to be used is M20 concrete. So if you go and see this clause number 6.1.2 of IS 456 2000, in this clause you will find that the minimum grade of concrete to be used in reinforced concrete structures is M20, and that is for mild exposure. So these two are the grades of concrete and steel that we will assume. Now let us find the effective span or L effective of our beam. We are given that the beam is a simply supported beam. So if you look at clause 22.2a of IS 456, in that clause what it says is that the effective span is the lower of, that means the lesser value of either the clear span plus effective depth or the center to center distance between two supports. We discussed about this effective span in our previous lecture also. Let us find this clear span first. What is the clear span? The value of this clear span will be the center to center distance between the supports, which is 8000 mm, minus half the width of brick wall on one side 300 by 2 minus half the width of brick wall on another side 300 by 2. That means we are subtracting this part here and this part. So this comes out to be 7700 mm. Now we need to determine the effective depth. So to determine the effective depth, we will look at in detail in another step also. But to determine the effective depth, IS clause gives us the span to effective depth ratios for different types of beams. So for simply supported beams, the span to effective depth ratio is 20. Now, considering this, you can find the effective depth as span over 20. Our span is 8000 mm 20. That means the effective depth comes out to be 400 mm. Now considering this, let us find the L effective. L effective will be lower of One is sorry, clear span plus effective depth. That means 7700 plus 400, and this comes out to be 8100 mm, where another center to center distance between supports is 8000 mm. So this is the lower value, hence our effective depth we will take as 8000 mm. Now in the third step, let us determine the percentage of steel reinforcement that we will be using. So the percentage of steel reinforcement to be provided is needed to determine the modification factor which is required to calculate the effective depth. That means using this percentage of steel reinforcement, we will calculate different modification factor as we discussed in our previous lectures, and using this modification factor we have to determine the actual value of DEI. So this percentage of steel reinforcement, one general provision is to keep about 75 to 80% of the limiting value of steel reinforcement. So to ensure ductile failure, we follow generally this provision, 75 to 80% of PT limiting. So to determine the value of PT limiting, we have discussed in our previous lectures for Fe 415 grade of steel that we have assumed here, PT limiting is given by 19.82 into FCK over Fy. So this coefficient type of new number that you see here, this is dependent on the grade of steel that you are choosing. So this 19.82 is for Fe 415. Hence, this you get is 20 over 415. This comes out to be 0.96. So 0.96% is the limiting value of percentage of steel reinforcement. Hence, the percentage of steel to be provided is assumed as, let us say we are providing 75% of 0.96. So this comes out to be 0.72. So now that we know the percentage of steel reinforcement, let us determine the actual effective depth. So in number 4, we will calculate the effective depth D. So we got the basic value of span to effective depth ratio is 20, and from that we got the value of effective depth is 400 mm. But as we discussed in our theoretical lectures, this effective depth value is modified based on the percentage of steel reinforcement that we have provided in our rectangular beam here. So let me go to that graph in my lecture here first. If you see this graph here, this is the modification factor for tension reinforcement. We have different curves for FS. FS is the stress in steel, and that is given by 0.58 Fy into area of cross section of steel provided over area of cross section of steel provided, required above and provided. So we will draw our vertical line from percentage of tension reinforcement in x-axis to that required FS curve, and from that FS curve we will draw a horizontal line to this y-axis to get the modification factor. So let us first determine this FS here. So FS is given, the formula is 0.F8 Fy into area of cross section of steel required over area of cross section of steel provided. So we assume that the area of steel provided and required is the same here, so that this ratio turns out to be 1. Hence the value of Fs is 0.58 into Fy, that means 415. So the value of Fs is 240.7 Newton per millimeter square. So using this value of Fs, we have to determine the modification factor. So let me just do it quickly here. Our percentage of steel reinforcement is 0.72 and the Fs value is 240.7. So 0.72 will be somewhere here, and Fs 240 curve, we will choose this curve here. So if we draw a line in such a way and then draw a horizontal line like this, our modification factor comes out to be nearly equal to 1.1. So we will use this modification factor here, so that our now effective depth becomes, first our span to effective depth ratio now becomes, the basic value is 20 into 1.1, which is our modification factor. This comes out to be 22. Accordingly, our effective depth now becomes 8000 over 22, which we get is 363.63 mm. Let's say this is 365 mm. So now, since this value of effective depth is different from the effective depth assumed at the beginning, that means this 400 mm. Now let us check the effective span once again. Effective span will be either lower of the clear span 7700 plus the effective depth 365, which comes out to be 8065 mm, or the center to center distance between supports, which is 8000 mm. So our effective span has not changed. It is equal to 8000 mm now also. Now we got the effective depth. Let us assume that our cover is equal to 50 mm, so that we get the total depth is 365 plus 50 equals to 415 mm. So we determine the effective depth here. Now let us determine the width of our beam. Let us assume that the width of our beam is 250 mm from general design considerations, so that if we determine the B by D ratio, this comes out to be 250 mm upon 415, which is nearly equal to 0.60. Hence it's okay. Now we will determine the total loads and bending moment. So there are two loads here. One we call the dead load, which is the self weight of the beam, and another is the imposed load, whose value is given in the question. So to determine the dead load, let us first assume the unit weight of reinforced concrete is 25 kilonewton per meter cube into the depth of our beam is 415 mm, so 0.415 meter into the width of our beam, which is 250 mm, that means 0.25 mm. You get the dead load to be 2.59 kilonewton per meter. The imposed load is given in question as 7 kilonewton per meter. So total load comes out to be 2.59 plus 7, which is 9.59 kilonewton meter. Now we have to convert this total load into factored load. Our factor of safety, or our partial safety factor for dead load and imposed load, is 1.5. So we will multiply it by 1.5 into 9.59. This comes out to be nearly equal to 14.385 meter kilonewton per meter. This is our factored load. Using this factored load, we will determine the factored bending moment, which is 14.385 into the span of our beam, that is 8 meter. This comes out to be 115.08 kilonewton per meter. So currently I am just using the force into distance formula to calculate bending moment. If you are given uniformly distributed load, for example like this, then you may even calculate the maximum bending moment based on your principles of statics, and then you can calculate the factored bending moment also. So in this way you calculate the factored load and factored bending moment. Now in the 7th step we will check for the effective depth D. Check for effective depth D. So this is done because it is desirable that we want to design the beam as under reinforced so that the ductility is ensured with stale stress reaching the design value. So let us now determine the limiting effective depth, and that limiting effective depth is determined when xu equals to xu max, and this factored moment that we just got is equal to the limiting moment, that is 115.08 kilonewton per meter. So if we suppose that this factored bending moment is our limiting moment, then we can calculate the value of xu max. So our formula is mu limiting is given by 0.36 xu max over d 1 minus 0.42 xu max over d into bd square fck. Now in this equation we have the value of everything except xu max over d. So xu max over d, if you remember from our lecture classes, this value is 0.479 or 0.48 for Fy equals to 415 Newton per millimeter square. So now use these values. Mu limiting is 115.08. To convert it into Newton millimeter, multiply by 10 to the power 6, 0.36 into 0.48, 1 minus 0.42 into 0.48, bd square into 20. This gives us the value of d as 408.76 millimeter. So now let us revise the value of d is 408.76, that means nearly equal to 410 mm from our earlier value of 365 mm that we got here. So that now our total depth becomes 410 plus 50 equals to 460 mm. Okay, this is covered completely. I will again continue here. So this is a long question. I am going in very detail here, so it will take some time to complete. So have patience and watch the complete video. That is what I want to say. Now we have determined and revised the effective and total depth. Now let us calculate the area of steel. Area of steel AST. So as I talked about in the very beginning, all of the parameters that we have to determine during the design of our reinforced concrete beam are interrelated, and the determination of one parameter may affect another, so that when we are designing, during our design steps, we may have to revise the value of some parameters also. We will do that after some time. Let us just look here. So our effective depth of beam has been revised to 410 mm from the limiting moment carrying capacity of the beam. Here we use the formula for mu limiting and we revise the effective depth of our beam. So that increasing the depth to 410 mm from our initial effective depth of 365 mm has raised the limiting moment carrying capacity of our beam to our design factored moment of 115 plus 0.08 kilonewton per meter. Remember, to determine this effective depth, we chose our design factored bending moment as our limiting moment. And you saw that to resist this much amount of moment, an effective depth of 410 mm was necessary. And if we had used only 365 mm depth as we determined initially, then that depth would not have been sufficient. So increasing the effective depth to 410 mm also has raised the moment carrying capacity of our beam to 115.08 kilonewton per meter. So now the area of steel is to be calculated from the moment equation, and that moment equation is used when steel is ensured to reach the design stress of 0.87 Fy. That means our equation to determine the area of steel will be 0.87 Fy ASTD 1 minus ASTFy over FCKBD. We have already discussed all of these formulas in our theoretical classes, so if you have any confusion, please revisit those lectures. So in this equation, everything is known except the value of AST. So if you put the value of everything, then we will get a quadratic equation in AST. So for that quadratic equation, we will get two values for AST, and we always have to take the lower value. So let me just replace all these symbols with their values. 0.87 into 415 into AST. Now here D we have to use the revised depth, which is 410 mm into 1 minus AST into 450 divided by 20 into 250, which is the width, and 410, which is the depth. So rearrange this equation, you will get a quadratic equation in terms of AST, and solve that quadratic equation. You will get the value of AST as 966.52 millimeter square, and another value you will get is 3973.24 millimeter square. So in this way you get the two values for AST. So what happens is that we have to take the lower value of AST here, because the lower value of the area of steel gives us the right value of XU here. If we determine the value of XU, then if you use the lower value of AST, which is 966 here, then we can determine the right value of XU. You can check that also, but here I'm just using this lower value. So let us use AST as 966.52 millimeter square. If you convert it into the percentage of steel reinforcement, you will get the value of percentage as 966.52 into 100 over B into D, which is 250 into 410, and this comes out to be 0.94 percentage. So remember that initially we assumed our percentage of steel to be 0.72 in step 3 here, but the actual value of steel that we will be using now is 0.94 percentage. So this percentage is higher than the initial assumed percentage of 0.72 percentage. Now when our percentage of steel reinforcement is increased, we have to maintain that by providing a higher effective depth. Now again we have to revise the higher effective depth here. So in step 9, we will increase effective depth and we will calculate new AST. Okay, let us suppose that now our effective depth is increased to 450 mm from 410 mm that we got here. So this is our effective depth. Now again use the same equation here. This equation that we use to determine the value of mu, except that now the value of D will be changed here. So using that equation again, we get this 115.08 into 10 to the power 6 Newton millimeter, 0.87 into 415 into AST. Now the value of D becomes 450 multiplied by 1 minus AST into 415 divided by 20 into 250 into 450. So again, this is a quadratic equation in AST. If you perform calculation, the value of AST you will get is 837.75 millimeter square. Now you can see that by increasing the effective depth, we have decreased the amount of steel reinforcement from 966 here to 837 here. If you convert it into percentage, you will get is 837.75 into 100 over 250 into 450, and this becomes equal to 0.446 percentage, which we can say that this is nearly equal to the initial assumed percentage of 0.72 percentage. So now our initial assumption and our calculation coincide and it's okay. So finally, let us have D equals to 450 mm. By adding a cover of 50 mm, the total depth will be 500 mm. The width of our beam will be 250 mm. And the value of AST will be 837.75 millimeter square. So remember that for any design problem, this increase of depth that we did here, this is obligatory to satisfy the deflection and other requirements. So moreover, what happens is that by obtaining AST, that means this steel reinforcement area with increased depth, we will ensure that our beam is under reinforced and we will ensure ductility in our structure. So this is obligatory. So now it seems that our design is complete and everything is okay. But remember that once we have increased the effective depth of our beam to 450 mm from our initial values, we have now increased the self weight of the beam and we have increased the factored load and factored bending moment in that way. So there will be further change in this AST value because of the increased dead load. We will do that in step 10 here. So our revised dead load is the unit weight of concrete 25 into the width of our beam 0.25 meter into the depth of our beam, which is now 500 mm total depth, so 0.5. This comes out to be 3.125 kilonewton per meter. If you remember previously, we adopted the total depth is 450 mm and only got the dead load as 2.59 kilonewton per meter, but now this has increased to 3.125 kilonewton per meter. Our imposed load remains the same, 7 kilonewton per meter. So our total factored load is now partial safety factor 1.5 into 3.125 plus 7, which comes out to be 15.1875 kilonewton meter, and thus our factored moment is 15.1875 into 8, that is the span, which comes out to be 121.5 kilonewton meter. This is greater than the initial factored moment of 118 kilonewton meter. So the limiting moment that our beam can carry is obtained by our formula that we discussed in our lecture. We discussed there that mu limiting over BD square is given as 2.76 for our FE 415 grade steel. So that now FU limiting becomes 2.76 into B, which is 250, into effective depth 450 square Newton millimeter. From this we get the value of mu limiting, which comes out to be 139.72 kilonewton meter. So this value of limiting moment is greater than our factored design bending moment of 121.5 kilonewton meter. We had to perform and check this calculation because our beam that we designed was not for this increased dead load as in the previous case. But since our dead load has increased here, that has caused an increase in the design factored bending moment. And we have to check whether the current section of our beam that is using has the limiting moment greater than this value of design factored bending moment. So we calculated the limiting carrying capacity of this beam, we can say that, and that limiting moment comes out to be greater than our design factored bending moment, so that we can say that our beam is still under reinforced beam. Now let us determine the value of AST for our design factored bending moment of 121.5 kilonewton meter. We use this formula here, 0.87 Fy ASTD 1 minus AST Fy over FCK BD. Now perform the calculation in a similar manner. We have everything except AST. Fy is 415, D means now 450 mm, B is 250 mm, FCK is 20. Then you get the value of AST again is 895.84 millimeter square. This you perform in a similar manner. You will get a quadratic equation in AST and adopt the lower value that you get as answer. So our area of tensile reinforcement or percentage of tensile steel reinforcement based on this area comes out to be 0.7963%. So this 7963% is 83% of PT limiting. So it's okay for now. So this is our final area of tensile reinforcement. Finally, our final design results. The width of our beam is 250 mm. The effective depth is 450 mm. The total depth is 450 plus 50, 500 mm. And the area of tensile steel reinforcement is 895.84 millimeter square. So if you use two 20 dia bars and then two 14 dia bars, the area of our reinforcement comes out to be 935 mm square. So this value is greater than our required value of 895 mm square, not very much greater, a little greater. So we can use this two 20 dia bars and two 14 mm dia bars. So this is our design results. If you want, you can draw the section of the beam also. So there will be holder bars at the compression zone here. We don't have to design them. They are just nominal bars given to hold our stirrups, which are our shear reinforcement bars. Let us say this is our stirrup, and we have two 20 mm dia bars and two 14 mm dia bars in this way. So our effective depth will be 450 mm. Our total depth will be 500 mm, and the width of our beam will be 250 mm. So this is our final design results. So this brings us to the end of our tutorial class on design of singly reinforced rectangular section. Now, this is a rather long process and a long numerical because of the various steps and various revision of parameters that you have to do based on your design step. Another easy way to perform this or to do this numerical might be to use the design charts that is given by our design aids. If possible, we will look at the same problem that we did today, and we will try to solve this problem using our design charts in our next lecture. and then we will start with the design of doubly reinforced beams. So we will meet again soon in our next lecture. Till then, stay safe and thank you.